So this is the fourth session on the topic music through Matlab, and we are going to study ADSR envelope in this session. Now previously we have studied half sine wave, how to use it as an envelope, that was studied. However, this particular envelope has very little flexibility, whereas if you use ADSR envelope, it has much better flexibility. So let us first of all see what this ADSR stands for. So the long form is attack, decay, sustain and release. This is the long form. In order to get better understanding of this, let us look at the graph. So we have plotted time on the x-axis and the amplitude of the envelope on the y-axis. And you can see the first part of this is a straight line starting from 0 going to 1 in a very short amount of time. Okay, if you consider the total time of this as 1 second, in this particular example it is 1 second, then this time taken by this rising portion will be just about 2%. So that is attack. Then you have a small sustain, and this small sustain may occupy a time which is just about 4% of this time, total time. So small sustain is 4%. Then you have decay corresponding to this term here, and this also occupies 4% of this total time. And in decay, of course, it changes from 1 to 0.9. Then you have a phase which is called as a sustain phase. So sustain might give rise to thinking that this is completely constant. That is not necessarily so. For certain envelopes this could be constant, but for certain envelopes this could be changing. In this particular example it is changing from 0.9 to 0.45, and this is the longest phase of this envelope, 88% of the time. Finally release, in which case it goes from 0.45 to 0 in a short amount of time, that is 2%. And of course all these percentages must total to 100%, and you can check that easily, it does indeed. And when we say, so in sustain phase I have already said amplitude drops to 45% for plucked instrument, but for bowed instrument this is going to be constant. Okay, and when we talk of percentage, I have already clarified, but let me repeat that percentage refers to the percentage of the duration of the note, which in this particular case was 1 second. Alright. Next, the question is, how do we generate this? So in order to understand that, we first study a statement which is called as a linspace statement. And this is the format of this statement. So y equal to linspace x1 to x2, and n is the third parameter. So this generates n points. For example, if n is equal to 100, this will generate 100 samples. And it will start with the values specified in x1. For example, if this is 0, it will start from 0. And if this is 1, it will go from 0 to 1, and 100 points total. Okay. So what is the spacing between the consecutive points? So the spacing between the points is x2 minus x1 upon n minus 1. So let me give you a concrete example of this. Suppose you execute a command linspace 0 to 1. So the starting value is 0, the ending value is 1, and the total number of points are 11. So therefore the spacing is x2 minus x1, which is 1 minus 0, that is 1, divided by 11 minus 1, that is 10. So 1 by 10, that is 0.1. So start with 0, 0.1, then 0.2, again the spacing is 0.1, 0.3, 0.4, all the way up to 1. That is the meaning of the linspace statement. You can of course practice this for various values of x1, x2 and n. Alright. Now the question is, using this linspace statement, how do we generate ADSR envelope? So we define a function en equal to envt, and I'll show you the complete program for the function in the next slide. but here we are going to study the algorithm itself. So envelope is the name of the function, envelope, T is the input array, okay, and En is the output array. Okay, so how do we generate this? We want to generate this. So first thing we do is find the number of samples in the, see, remember T is a entire vector. So for example, before calling this function, T may be defined as 0, 1 upon 22, 0, 50, D. Remember, we have done that before. So now first thing you do is find the length of T, that is the number of samples in T. For example, in this case, the total duration is 1 second. So it will mean that the total number of samples in T will be 22, 0, 50. That will be your T. The reason for finding the number of samples is that, remember, in linspace command, the last parameter is an integer. So that is why you need to do that. Then you want to generate 2% of this time of this. So 0.02 multiplied by T. But since you want an integer, you round this. So this will give you number of samples which correspond to 2% of the total number of samples that you have got. So once you have this, then you can generate the first line. So L1 will be linspace starting from 0 going to 1, and how many samples? T1, which are calculated from here, that is 2% of the total number of samples. Similarly, you can calculate the rest of them. So L2, for example, for L2 it is starting from 1 and ending on 1 itself. So here you will get entries for L2 from 1 to 1, and then this is 4%. So you will have to calculate 4% of T by another statement for L2. So similarly, you can calculate L3, L4, L5. Finally, concatenate all of them and get the envelope. Alright. So let us see the function itself now, the complete program for the function. It's now easy to understand. Function En is equal to envelope T. So you first find the length of T, then take 2% of T, round it up so that you get an integer. Then another value we had used was 4%. So T2 is 4% of T. Then we had 88%, that is the sustain phase. Now generate L1. So that is the attack 0 to 1. L2, that is a small sustain 1 to 1 T2. L3, that is a decay. So that goes from 1 to 0.9. This is the sustain phase. So that goes from 0.9 to 0.45. And 88%, that is T3 here. And finally you have the release, which goes from 0.45 to 0, T1. Then you concatenate them, and En is equal to A. Of course, I could have written En directly here. Anyway, in this case, it's written like this. So this array A is returned, okay, by specifying the value in En. Alright. One thing to note is that because of rounding operations, the number of samples in T and En might not be equal. In fact, you might get an error of say one sample or 2 samples. But generally there will be so as I said, generally there will be an error of 1 or 2 samples. But it is necessary to make them equal. Later on you will see that if you want to process 2 arrays, for example, you want to do pointwise multiplication of 2 arrays, then their lengths must be equal, otherwise the Matlab will produce an error. Also, if you want to plot say time versus the envelope, then unless the number of samples in both are same, you can't plot them. So therefore it is necessary to make them equal. So we write a function called equal which makes them equal. So next what we will study is what is the algorithm for this function equal. So let's see, y1 and y2 are the output arrays, x1 and x2 are the input arrays. So what is the algorithm? What is the technique? So x1 and x2 are input arrays. So what you do is you calculate the number of samples in x1 and compare them with the number of samples in x2. So if the number of samples in x1 are greater than that of x2, then what we do is and let's say this number is k, then we append k number of zeros to x2 because x2 is shorter than x1. So you elongate it so that its length is exactly equal to x1. But it may be that x2 number of samples are greater than that of x1. Again by a number say k, then we append k number of zeros to x1. But if both lengths are same, no appending is done. And then once this is done, then x1 is copied into y1 and x2 is copied into y2. So essentially note that y1 is same as x1, y2 is same as x2, but you have appended enough number of zeros so that the length of y1 and y2 are same, even though the length of x1 and x2 are not same. So this is the algorithm, this is the technique. So let us now see the complete program. So function y1 y2 equal to eq, that is the name of the function. Input parameters x1 array, x2 array. So you calculate length of the array, length of x1 and put it in a. Then calculate the length of x2, put it in t. If t is greater than a, it means x2's length is greater than x1. So you must append a number of zeros to x1. So you calculate this difference first, t minus a, and then for I equal to 1 to diff, you append the number of zeros which are required. Similarly, if t is less than a, then what you do is you append the number of zeros to x2. Once this appending is completed, and if this is not satisfied, this is not satisfied, it will mean that the lengths are equal and you don't have to do any appending. So at the end, now x1 is copied into y1, so y1 is x1, y2 is x2, and then you return. Okay. So now let us test the envelope and the EQ functions, equal functions. So as usual, clear the variables, clear the console, clear the figure, define the t vector. So 0, 1 upon 22, 0, 50, 0.5 seconds duration. This could be something else as well, but in this example I have taken 0.5 seconds duration. Then you call the function envelope and generate E. So E is equal to envelope t. Now when you do that, as we have seen, because of the rounding there might be an error and you want to check that. So what you do is you display the length of t, display the length of E, and in fact when the program is run, you will find that the length is slightly different. In one case it is 11,026, in the other case it is 11,027. So therefore now what you do is you use the equal function to make the arrays equal. So I am writing my output arrays also as t and e. It's not necessary, but I am writing them as that, and t and e are the inputs. So once they are made equal, you can plot. So you plot t versus e, the line width 1.5, then you put the grid on x label, y label, and you will get this output. So that tells you how to generate the envelope, and while generating the envelope you get problems, so you use an equal function. And in our later sessions we shall see how to use this envelope in order to generate a musical note with more flexibility. And that's all in this session.